Today on Reverse This Learn That, we're going to be looking at smoke detectors. While there are hundreds of guides and videos explaining the two types of sensors and how they work, I want to dig a little deeper. Before we start, let's address the basics of smoke detectors. There are two main types: ionization detectors, which use ionizing radiation, and photoelectric detectors, which use photocells. Ionization smoke detectors have an ionization chamber and a source of ionizing radiation. The source of ionizing radiation is a tiny quantity of americium-241. Within the ionization chamber, there are two plates about a centimeter apart. The battery of the detector applies a small voltage to the plates, charging one plate positive and the other plate negative. Alpha particles, constantly released from americium-241, knock electrons off of the atoms in the air, ionizing the oxygen and nitrogen atoms in the chamber, and cause positively charged oxygen and nitrogen atoms to bind to the negative plate and knocked off electrons to bind to the positive plate. This generates a small, continuous electrical current, and when smoke enters the ionization chamber, the smoke particles attach to the ions and prevent them from generating this electrical current, which triggers the smoke alarm. On the other hand, the main type of detector I will be focusing on is the photoelectric smoke detector, like this P1210 first alert smoke alarm. In most photoelectric smoke detectors, light is scattered by smoke particles onto a photocell, initiating the alarm. In the simple example, these detectors operate within a T-shaped chamber with a light-emitting diode, LED, that shoots a beam of light across a horizontal bar of a T-shaped chamber. A photocell, positioned at the bottom of the vertical base of the chamber, generates a current when it is exposed to light. Under smoke-free conditions, the light beam crosses the top of the chamber uninterrupted, not striking the photocell. When smoke is present, the light is scattered by smoke particles, and some of the light is directed down the vertical part, which strikes the photocell, triggering a current setting off the alarm. With the fundamental set of how the smoke detectors work, let's begin reversing and learn how this is achieved in the first alert smoke alarm. On the face of the alarm, we are not left with much to the imagination. Starting from the left is a push tab to interact with a button to silence or test the alarm, a slot to view the status LED, and another slot with access to the speaker. Flipping the alarm over, we have a mounting bracket that twist locks to the alarm's case and has multiple cutouts for various mounting options. With the mounting plate removed, the back of the alarm case is exposed, providing access to the alarm's activation switch, as well as paper instructions that are glued flush to the case. To gain access to the internal components of the smoke alarm, 4 screws are hidden behind the glued paper instructions that I've already taken the liberty to cut away. With the faceplate removed, the smoke alarm reveals that it's made up of 4 main components: a lithium battery, a PCB or printed circuit board, a speaker or buzzer where the sound is produced, and a hidden smoke chamber attached to the back of the circuit board. Reversing electronics can be similar to solving a puzzle by looking at the clues each of the components gives us. All electronics are part of or contain a circuit. The simple definition of a circuit is a complete or closed path through which electronic current can flow. In our case, it is the battery, the PCB or printed circuit board, and a buzzer. I prefer to go piece by piece and look for the start of the circuit, which tends to be the power source. In our smoke detector, we have what appears to be the lithium battery with the FDK Corporation markings on it. A quick web search will show that this is the FDK CR17335EG 3-volt lithium battery, which feeds our smoke detector circuit with power through the red, most likely positive, and black wire, most likely negative, that connect onto the jack located at the bottom face of the board. Now, the printed circuit board can be overwhelming at first glance as it floods you with a wealth of information. However, when hunting for the clues, the mystery can start to unravel relatively quickly. According to the almighty Wikipedia, a PCB or printed circuit board is a laminated sandwich structure of conductive and insulated layers. PCBs have 2 complementary functions. The first, to affix electronic components to them in designated locations on the outer layers by means of soldering, and the second, to provide reliable electrical connections between component terminals in a controlled manner, referred to as the PCB design. One of the first things I noticed was the notation noting the PCB board. While trying to look this up got me nowhere fast, I will note that circuit boards can be difficult to search as the manufacturer might not have any information or data sheets available for the exact PCB design that you're looking at. Rather than sinking my tie into the black hole going nowhere, I began to scan through the other markings on the PCB. While not all PCBs will have the same markings, the first alert board makes it easy to identify the different components used within their circuits. The tiny white letters located throughout the board are called reference designators, or as some call them, component tags. These do exactly as the name implies. They designate or tag the various components on the PCB. For example, U1 indicates the integrated circuit, R indicates a resistor, and RN or N indicates a resistor network, C for capacitors, D for diodes, and many more. Understanding these various designators can quickly translate the board components. I'll provide a link below with a reference to a standard reference designator list. Getting back to the board, the integrated circuit appears to be an important component as everything seems to run to it or from it. The integrated circuit is essentially a smaller electrical circuit on a semiconducting material performing the same function as the larger circuit, basically a circuit within a circuit. If you look a little closer on the markings on the integrated circuit, we can see RE46C190 printed on the face of the component, handing us another clue. After a quick web search for RE46C190 integrated circuit, the clue has led us to the answer sheet giving us the exact details of what we need and how to understand how these smoke detectors work. The RE46C190 is a low-power, low-voltage CMOS photoelectric type smoke detector integrated circuit. With minimal external components, this circuit will provide all of the required features for a photoelectric type smoke detector. The design incorporates a gain-selectable photoamplifier for use with an infrared emitter detector pair. The internal oscillator strobes power to the smoke detector circuitry every 10 seconds to keep a standby current to a minimum. If smoke is sensed, the detection rate is increased to verify an alarm condition. A check for low battery condition is performed every 86 seconds, and chamber integrity is tested once every 43 seconds when in standby. The datasheet goes into much more detail about typical circuit configurations, recommended placement in PCB construction, expected voltage, and much more. I'll leave a link in the description in case you're interested, but the content can get heavy rather quickly if you're not versed in electrical engineering lingo. Focusing back on the smoke detector's integrated circuit description, it mentioned two components we have not yet looked at: the smoke testing chamber and the temporal horn. Pulling the PCB out of the smoke detector housing, we can see a smoke chamber is mounted on the back side of the PCB. The smoke chamber features a fine mesh around the diameter of the chamber to prevent larger objects from sneaking in and causing false positive results. The chamber allows smoke to pass through these Z-shaped slits that also prevent unwanted light from entering. On the underside of the board is the bottom of the IR, or infrared emitter and detector. The first lens is the photodiode, or the IR detector, and the second is the infrared LED emitter. While this isn't exactly the T-shaped example that I gave in the beginning of the video, it operates in the same capacity. The infrared LED emits a signal out into the smoke chamber, and when smoke enters the chamber, deflects that infrared light into the photodiode, causing a spike in current which triggers the alarm. The final piece to the smoke detector is the temporal horn. After removing the horn from the PCB and the plastic housing, we are left with what looks like a simple metal disc with 3 wires attached to it and some odd circles on the back side of it. After a bit of research, these pieces are called piezoelectric transducers or piezoelectric sound components. Now, these devices and how they work deserve their own deeper dive video. In short, the ceramic plates that are glued to the metal plate prevent the metal from flexing in one direction. When the current is applied rapidly, this causes a sound when the alarm is triggered. When you put all these components together, you get life-saving technology that many of us take for granted, and if anything, only know them for the annoying mystery hunts they send us on during their low battery chirp notification state. This is Reverse This Learn That. I hope you learned something, and thanks for watching.